So the next piece we are talking about is the precise definition of a limit. Okay. I need to ask you guys something today. I just need you to be patient with me, okay? Because this is one of those things, there's no way to just like dip your toe in and ease into it. You just kind of have to jump in the water and eventually you'll start swimming and it'll be okay, all right? But you gotta be patient with me. Don't freak out on me. Don't start complaining and whining and saying you're never gonna get it. Just be patient. We're just gonna kind of jump in and we'll get back to the surface in a few minutes, okay? We're gonna take a couple days on this. So there are a few, we've been doing this limit and we have this rough idea of what it means. And then there is this actual definition, which has a lot of Greek letters in it and looks really confusing, that I have to teach you because if you go on to take higher levels of calculus, it circles back and you need it again. If you don't, you really never have to use this. So I have to teach it to you, but we're really not going to use it outside of these couple days in class, right? This is the type of thing that will probably be a bonus question on your test or quiz, not something that I'm really going to expect you to do a lot of, right? So I just need you to be patient with me. I have to show you because some people will go on and have to see this again. Most of you will not. Okay, so let's talk about this kind of function here. We have seen these piecewise functions before. And this one is basically just a line, 2x minus 1, but what's going to happen when x is 3? Yeah. Basically, if you drew your line, it's just, my graph is really skewed here. It's going to look like that, and it has just an open circle on it at that one point, and then it's just a closed circle also. So it's just a line with a hole in the middle. So we can see that as we're getting closer to 3, if you're approaching 3, then you are on that line itself. And so from what I told you about limits, we know we could really just plug in and that thing is approaching 5. But at 3 itself, we know it's equal to something different. And I've told you a limit doesn't care what happens at the point, just as we get close to it. So if I really wanted to be a little more precise about what's going on with my function, we could ask ourselves, how close to 3 does x have to be so that f of x, or the y, differs from 5 by less than 1/10? If this limit is actually 5, then I should be able to pick an amount. Say I want you to be within 1/10 of 5. And you should be able to tell me what kind of x's you would have to plug in to get that close. And I said, okay, I need to be even closer to 5. I need to be within 100. Then you guys should be able to find an x value that would get me within 100 of 5. So that's kind of our motivating question. It's like asking yourself, how close does x have to be to get my y to be this close? Okay, if you think about like manufacturing, if they're making parts for a car, does every single part coming off that assembly line, is it identical? No. But how close to the precise measurement does it have to be so that it will still fit on the car, right? Because we know there's error. Everything is not going to be perfect, but how close is close enough? So that's kind of the motivating question here. All right, so to measure the distance from 3, we subtract our x values, right? Absolute value is the distance. We know distance has to be positive. So we are going to look the distance between x and 3. We do the absolute value of that. The distance from my y to my 5, we do absolute value, so it's positive. So here's our first Greek letter. We have to find a number. That symbol is called delta. It's just a Greek letter. It's just a variable. So we have to find a delta. so that it says the distance between your function and 5 is less than a 10 if the distance between x and 3 is less than delta. So, does my x have to be within 100 or a 10 or what? We're finding that amount. Another way that we could be writing this is the absolute value of x is less than 1/10 if 0 is less than the absolute value of x minus 3 is less than delta. That's kind of redundant because we know absolute value is always greater than 0. So if you ever look in the book, because I'm sure you guys go home and read a lot to make sure I'm not lying to you, they use this a lot, but I don't usually because we know absolute value is already positive, so we don't really need the fact that it's greater than 0. Okay, so here I'm just kind of pulling this number from nowhere at the moment. You'll find it later. But I'm telling you, let's try 5/100. Okay, so if my x was in 5/100, then the distance between my function and 5, well, my function was the absolute value, or was the 2x minus 1. So if I plug that in for my function, combine like terms, you get the absolute value of 2x minus 6. You could take a 2 out of that. But I just said, let's pretend that x minus 3 is less than 5/100. So if I plug that in, we get the 1/10. So if you want your y to be within 1/10 of 5, that means you want to get a y value between 4.9 and 5.1. I'm telling you, all right, your x has to be within 5/100 of 3. So you need to pick something between 2.95 and 3.05. That's what we're going to do here. We're finding what kind of number would make that work. So that is the answer to this question. We would have to be within 5/100 of my x to make this work. All right, so this is the actual definition of a limit using epsilons and deltas, all kinds of Greek letters. So the limit of the function, which is what we've been calculating, says if for every number epsilon greater than 0, there is a delta greater than 0, such that the absolute value of x minus a is less, if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So it's saying we should be able to find a number so that the distance between x and the value we're approaching, if it falls within that window, then our y's fall within the window. Okay, another way to think about it, if we think about a graph, we're saying, okay, here's the a that we're approaching, and we're going to pick some range of values, x minus that amount and x plus that amount. And we have to pick that window so that our y's fall within this window around the real value. Another way of thinking about it, on this graph, okay, here's, if I want my y's to fall within this range, right, well, that hits here and here on my graph. So my x's would have to fall within there, down on the x-axis. So that's what we're doing. All right, so let's try, just to get a general idea, I want to use a graph to find a number delta so that if the absolute value of x minus 1 is less than delta, then the absolute value of x cubed minus 5x plus 6 minus 2 is less than 2/10. So we're going to find how close to our x we have to be. We're starting here. Let's simplify over here. We could, if we wanted to think about this, absolute value, if if I wanted to write that without the absolute value, that means it falls between a negative 0.2 and a positive 0.2. We did that in Algebra 2 and College Algebra, less same as an and. So if you want to write it without the absolute value, it goes between the negative and the positive. So then if I'm trying to get that function in the middle by itself, what would I need to do with my minus 2? So if I add 2, I get 1.8 is less than my function. It's less than 2.2. Let's grab a graphing calculator. Okay. I'm going to graph this function, x cubed minus 5x plus 6. And I want this to fall between 1.8 and 2.2, so I'm going to put those in as a y2 and a y3. So I made my middle part my y1, I did 1.8 as my y2, and 2.2 as my y3. So if we just zoom 6, look at, we're all kind of looking at the same thing there. That's my function. There's 1.8, and there's 2.2. Now I can't see this very well, so I might adjust my window to help me a little bit. My x's, let's just go from 0 to 5. My y's, we're looking between 1.8 and 2.2, so let's just go 0 to 5 on those as well. So here's my little function. There's 1.8, and there's 2.2. I want my function to fall between those values. There's actually two separate ones. Let's just find this first little window here. So if we want to be between there, we need to find out where this function meets my curve, right? We can go to second, hit the trace button, and we want to intersect number 5. The first curve, it tells you up at the top, it's the x cubed, which is what we want, so just hit enter. Second curve, I want to be on my top line, so I'm just going to hit the down arrow and it'll jump up there for me. And guess, you kind of have to tell your calculator which point you want, so get close to that one. And it tells me 0.91142. Okay, so that's the smallest my x can be. If I want to find the biggest, we repeat that. So we go to second, trace, intersect again. First curve, we want the graph again. Second curve, it went to it automatically, the 1.8, and I want that first point there, and that's 1.1240. So basically, what we found, if I want my y's to be within 2/10 of 2, that meant my y had to be between 1.8 and 2.2. And you can make that happen if you pick an x between these, 0.9 and 1.1. So right now we're just kind of working backwards. We're figuring out what x value would give us the requirement we need. So all of this is just kind of our motivation, our thought process. This isn't actually what I'm going to have you do on these problems. This is just trying to understand what we're doing. We need our y's to be within a certain window, so you have to figure out what x's correspond to that window. Now, in general, we would like to be able to calculate that quickly. You know, if I need this one to be within 2/10, but then I turn around the next one I need it to be within 1/10, I don't want to have to recalculate all that on my calculator. I would like a formula for how that happens. And so that is what's called the epsilon delta definition of a limit. So this is the stuff. We're going to do it. We're going to practice. All of these are going to kind of look the same. I've already told you this is like a bonus type question that I would give you. Outside of this section, we're never using this again unless you go on and you have to take, you know, advanced calculus, those types of things. But I have to show it to you so that if you do, you've seen it before. I'm going to skip that next one. We're just going to come to this. So, to use my epsilon delta definition, we are going to start with an epsilon. It'll always be positive. And we're going to use the definition of a limit. So our function, the distance between my function and limit has to be less than epsilon. We'll use that to find a formula for how close our x has to be. And then we will prove that. So, the rest of the day today, we are just going to walk through these problems. And it's going to be kind of like a cookie cutter problem. We're doing the same thing every time. We're just practicing how this definition works. So if you think about the definition of a limit that I gave you, is right here. So I am going to ask you to prove something. And we have to use that definition to do so. So in order to prove it, you have to show that the definition works. So here is our first one. I want to prove limit as x approaches 3 of 4x minus 5 equals 7. Okay, we know this is true because I've told you you can plug in the 3, you get 12 minus 5, it's 7. We're good, we believe that. If I want to prove that it's true, we have to show the definition works. And the definition says, if this is really the limit, you can get your y value as close to 7 as you want just by making your x get closer to the 3. But we just have to figure out how close to 3 do I have to be to make my y close to 7. So we'll start with kind of our goal here. And I'm going to write this down every time because that kind of shows me if I'm on the right track. Definition says if the absolute value, looking back, the absolute value of, I told you you didn't really have to do that part, so x minus a is less than delta. So in my problem, x minus a is the value your x is approaching. And I just have my delta. Then, if you look back at your definition, it says the absolute value of f of x. F of x is your function, minus your limit, my limit is my 7, is less than epsilon, this curve looking e. So in other words, that's my a, this is my function, this is my limit. I'm plugging those things in. So we are done when we have proven this statement is true. That is my goal. To do that, we have to first find delta. Excuse me. Okay. To find our delta, we are actually going to work backwards from the answer. Okay, we're going to work backwards from here. So if I take that, absolute value of 4x minus 5 minus 7 is less than epsilon. Actually, let's not even put the epsilon yet. Let's just work with this part for a moment. Make it a little less confusing. If I want to simplify in here, combine like terms, so you get 4x minus 12. What could you do with that? Take out a 4. Can it come all the way out in front of the absolute value? It's positive, so absolutely. Okay. Have we seen this x minus 3 before? Yeah. All right. We know that this piece has to be less than epsilon, right? So this thing is less than epsilon. If you divide that 4 over, this is what we are going to use for our delta. This is kind of a formula. So basically what this is saying is if I want my y's to be within 1 of 7, then I need my x's to be 1 divided by 4, 1/4 away from 3. So my x's would have to be between 2.75 and 3.25. If you wanted your y's to be within, just ahead of you, I appreciate that. If you want your y's to be within half of 7, so if you wanted it to be between 6.5 and 7.5, so if I took my 0.5 divided by 4, we get 1/8. My x's would have to be within 1/8 of 3. 2.7825 and so forth. So we have basically, this is just our scratch work to figure out, if you give me an amount for y, I can tell you how close x has to be. That's the work part. Now we have to prove it. So now we are going to show this goal here. So step 2 is the proof. The first thing you're going to do in this is always start out stating what we found up here. So we are going to let delta be epsilon over 4. So to find my x's, you take that window on your y's and divide by 4. Then we are going to state the first part of what we're trying to prove. So if the absolute value of x minus 3 is less than delta, then we'll go ahead, let's just even state this part. The absolute value of 4x minus 5 minus 7. And we are done when we can get a less than and an epsilon into our problem. Okay. This seems really sketchy, I know, because we're just kind of writing down everything that we want, but we're getting the first part. This is kind of what's called a math proof. So you have to state that first part, and then we're trying to prove it's less than epsilon. So now we're really just repeating what we did up here. Here, this is like our scratch work. So we're just going to repeat that. So this is the absolute value of 4x minus 12. And you can take out that 4 just like we did above. But we said the absolute value of x minus 3 was less than delta. So 4 times this absolute value is less than 4. I'm just going to plug in that delta for my absolute value. So right now, I have my less than sign. All we have to do is get our epsilon and we're done. But what did we say we are going to let delta equal? Epsilon over 4, which is epsilon. I got my less than, I got my epsilon. We are done. That's all you have to prove. So that means the limit as x approaches 3 of the 4x minus 5 minus 7, or sorry, of the 4x minus 5 equals 7. Okay, I know it seems really strange because we're really kind of doing the same thing twice. The first part, step 1, was kind of our work to figure out what's going to work, and step 2 is proving it. I know this is really abstract because you guys have never done proofs like this before. We're just kind of trying to get a feel for it. I am not going to be throwing any tricks in here, guys. So every problem we look like is just going to look like this. Okay. All right. Is your mind blown yet? You totally lost? It's scary looking, I know. But the good news is they're all going to be the same. Okay, so we're just going to keep working through these. Same process every time. So here's our next one. First thing I like to do is write down my goal. That's the definition of a limit. So it's if the absolute value of x minus a is less than delta, then the absolute value of my function minus my limit, which was 10, is less than epsilon. So that's my goal. When I get that, I'm done. Second thing we do is our work. We have to figure out what delta can be. So to find our delta, we are going to work backwards from this. Okay, there's different ways of writing it. If it is more clear for you, instead of going like side to side, do you guys want me to work down? Would that make it a little bit easier? So essentially, I'm working from this statement right here. So if you work inside that absolute value, you get 13x minus 39. So that's less than epsilon. What can you do now? Take out 13, it's positive, so it comes all the way out. And then what should I do? Divide the 13. So that means I want my delta to be epsilon over 13. So that's your goal. Step 1 is to find delta. Step 2 is the proof. When you do your proof, every time you're going to go back up to your goal and you are just regurgitating all of this. And then we have to prove the less than epsilon. So the first thing I'm going to write down is that statement. But I do have to also state what my delta is. So I'm going to say, let delta equal epsilon over 13. And then I'm going to write that sentence. If the absolute value of x minus 3 is less than delta, then the absolute value of my function minus my limit. And now I have to get a less than and an epsilon in my problem. So we're just repeating what we did above in our scratch book. So that's the absolute value of 13x minus 39. You can take out your 13. But I already said that x minus 3 is less than delta. So 13 times the absolute value of x minus 3 is less than 13 delta. So I've got my less than in my problem. Now all we need is to get the epsilon. What can we do at this point? Plug it in. We already said delta was epsilon over 13. So it's epsilon. And we're done. Is it better? I know it probably doesn't make sense yet. Is it better? Are we like swimming back to the surface maybe? Still in the still underwater, but getting closer. I'm just gonna do more. First thing I like to do is write my goal. So our goal is to, remember we're just doing that definition. If the absolute value of x minus a, my a is 0, is less than delta, then the absolute value of f of x, so your function, minus your limit, is less than epsilon. Okay, so step 1 is the scratch work, find delta. We start from this second part, so we're just working backwards. So subtracting 0, we could just drop that. Absolute value just makes it positive. Does that matter? Does it matter if you make it positive before or after you do the cube root? No. So what I could do is bring my absolute value under my radical. How would I get my absolute value of x by itself? How could I get rid of my cube root? Cube each side. So the absolute value of x is less than epsilon cubed. So I need my delta to be, that was a crazy epsilon, epsilon cubed. So step 2 is when we prove this. We start with the delta equal epsilon cubed. And then we're writing this piece. The absolute value of x minus 0 is less than delta. And the absolute value of my function minus my limit Now, we're just doing the same thing we did before. So we know if we subtract 0, we can just drop that. We can bring the absolute value underneath. Now, is the absolute value of x the same as the absolute value of x minus 0? Yes. So I can replace this with my delta. So since that was less than delta, this would be less than the cube root of delta. So I've got my less than. Now I need my epsilon. Delta is epsilon cubed, so that's the cube root of epsilon cubed, which is epsilon. That's what we were trying to prove. I'll probably do one more today, and I'll save one to start us off tomorrow. So, my goal, the definition. If the absolute value of x minus a, what's my a? Minus -3 would be plus 3 is less than delta. And then the absolute value of f of x, that's just your function, minus your limit, that's -30, so it becomes plus 30, is less than epsilon. So first we find our delta. We start with that second half. So inside we can combine like terms. What can you do now? And then what? So I need my delta to equal epsilon over 7. Step 2 is approved. So you have to state what delta equals. And we state what we're trying to prove. The absolute value of x plus 3 is less than delta, and the absolute value of 7x minus 9 plus 30 . So then if I work that out, you get 7x plus 21, take out your 7. But we've already said that the absolute value of x plus 3 is less than delta, so that's less than 7 delta. And we said delta was epsilon over 7, so that's 7 times epsilon over 7, which is our epsilon.